So, welcome back friends. So, we have been discussing about Majorana fermions as a special solution of Dirac equation. Okay. So, what we have seen is this Majorana fermions were considered to be uh, not very interesting till 1960s or 70s in particle physics. Around the same time also in superconducting theory in condensed matter system essentially. But the discovery of the Maranoff solutions were happened soon after the Dirac equation itself, within a couple of years essentially. In 1933, Maranoff found out these solutions uh, which are akin to the situation where the wave function is completely real. Okay. So, these Maranoff modes correspond to the case in which where all the gamma matrices are completely imaginary, uh, and uh, and so the real part of the gamma matrices vanishes. Okay. And then we discussed how to write down the most general form of the condition that what we call as the Marona condition, which is essentially that psi should be equivalent to psi c, where c is the wave function after the operation of the c operator, the charge conjugation operator acting on the psi itself essentially. So, the c, okay. So, we can start with this condition actually in many textbooks and many places. We start with the condition to derive the Majorana solutions that psi is equal to psi c. So, you can start with in the modern most of the modern textbooks what happens is C is considered to be a unitary operator, and C is also considered to is the discrete symmetry of the Dirac equation and the Dirac Hamiltonian. And it turns out that you study all these discrete symmetries along with the Lorentz symmetry of the Dirac equation, and then put it then take the condition psi is equal to psi c to derive the Majorana fermion solutions essentially. So, these Majorana fermion solutions as we have seen, they are two component, they have reduced number of degrees of freedom, and the implications are that the particle and antiparticle wave functions are the same, and that is because they are real wave functions, and it's they have to be neutral. They have to be neutral because the quantum numbers of the particle and antiparticle should be equal. So, which does not happen solely if the particles are neutral. So, in this case we considered essentially two particular scenarios, two particular examples in which the particle and antiparticle particle are the same, could be same, and they could have the same they are neutral. So, the two examples we considered are, one of them is neutrino. Where is it? I am just searching for it. Yes, one of them is a neutrino, another of them is a neutron essentially. Then there are several other examples in more complicated theories, in BSM theories like supersymmetric theories have a lot of neutral fermions which are all Majorana fermions, and then there are several other cases in which you can have this kind of scenarios. Okay. And if you go to further theories like string theory and so on, so you will also have several examples. Well, now let us look at a little bit about these examples like I promised. So, I will consider I will not go into the details because the details are very involved, and you need to know a full lot of theory and everything. But I will just try to give you a heuristic idea about one example in particle physics, in another example in condensed matter systems essentially. So, for the first case, let us look at the example of neutrinos Let us look at the one example of neutrinos in particle physics. So, neutrinos are introduced in Standard Model or in the Fermi theory as massless particles. But in 90, so they have been considered to be massless particles. So, they are always described by Weyl fermions. They are always described by Weyl fermions in the Standard Model in the Fermi theory of beta decay. So, now what happens is that if the neutrinos now in 19 but this assumes that neutrinos are massless. But experiments proved contrary. So, there have been this fantastic experiments which have been proved contrary. So, in 1998 there are these experiments called under the name of Super Kamiokande, which showed that neutrinos have masses. So, the moment neutrinos have masses, the question then arises whether they are Dirac-like masses or they are Majorana-like masses. Now, let me just go back in the previous case. Now, when we derived this in two equations for the Majorana case, you remember we derived these two equations for the Majorana case, putting it back. These two equations in the Majorana case, okay, we had two different spinors essentially. One is a psi r and one is a psi l, which has its own set of solutions, two component solutions. So, these are completely decoupled, and that is the reason why I consider their masses to be completely different essentially. Mr could be a different mass, Ml could be a different mass. Now, Mr could be a different mass. Now, in general, then I mentioned that so the moment the mass is 0, they become Weyl fermions, and these two equations are equivalent to each other. Okay, these two equations just become Weyl fermion equations. Now, in the limit the mass is equivalent to Mr is equal to Ml, then they form a Dirac spinor. They form a Dirac spinor with psi l is equal to psi r I sigma 2 sigma psi r star. So, they end up forming a Dirac spinor. So, two Majorana fermions can form a Dirac spinor. That is the thing which is all explained. But starting from a Dirac spinor, you can imagine that you can decompose it into two Majorana spinors in this particular fashion, under the assumption that MD has always been decoupled into two Mr and Ml essentially under the okay. When you are doing the decomposition starting from a Dirac spinor to two Majorana spinors, you have to consider the situation that Mr and Ml need not be of the same masses. That is the reason when you have in two independent solutions that they need not form a Majorana case essentially. Okay, that side aspect. Now, this tells you that Majorana nature is associated always with the mass. The moment if they are massless, you cannot tell whether they are, in principle it becomes hard, because we have the way we have written it in terms of Weyl fermions, because in this particular system, in the system of Standard Model and weak interactions, neutrinos appear, all the fermions appear as Weyl fermions. So, that is the reason why we are so hell bent about introducing this Weyl fermion notation and understanding a Majorana and Dirac picture from this directly from terms of the Weyl fermion picture. Okay. So, in the Standard Model we start with massless particles, and so that is so the neutrinos participate in weak interactions, or which are responsible for things like fermion, beta decay and nucleon decay and so on. So, and you see that they appear as wild fermions. So once they appear as wild fermions, so you have to understand that unless I put in unless the mass term appears to be non-zero, you cannot distinguish between them whether they are Dirac or Majorana. And given that neutrinos are neutral, they can be either Dirac or Majorana particles. Okay. So they can be either Dirac or Majorana particles. In the case when they are Dirac, and as of now no experiment has so far discovered this particular aspect. This is still an open question. This is still an open question. Which is not yet answered whether neutrinos are Dirac or Majorana. Now neutrinos are very interesting objects. They travel with almost close to speed of light. So these experiments like Super Kamiokande and everything, they are almost like astrophysical experiments because these are quantum objects but traveling astrophysical distances. So you have particles traveling from say the sun and being detected on the earth, the sun. Okay, these are particles produced in nuclear fusion in the sun, and they travel all the way to the earth, and their properties are being discovered by this propagation from the sun and how they propagate inside the sun and from the sun to the earth, the distance how they travel, and from that particular aspect their properties are discovered, and they undergo something called the neutrino oscillations. Where in the sun they are mostly produced as electron neutrinos, and these get converted into muon neutrino plus tau neutrino, linear combination of muon neutrino and tau neutrino essentially. Okay, linear combinations of muon and tau neutrinos, and this has been detected in experiments, and this kind of neutrino oscillation phenomena is only possible if neutrinos have masses. So neutrino oscillations implies neutrinos have masses, and neutrinos have masses implies that the question is whether there could be Dirac or Majorana. Now there are a lot of experiments which are detected which are designed to probe the nature of these neutrinos. Essentially one particular experiment which tells you whether the neutrinos are Dirac or Majorana are called neutrinoless double beta decay. So this is a very interesting experiment, but this process can happen. This process can happen only if neutrinos are Majorana. So if you detect this process, okay, the detection of this process is very sensitive. It is an extremely rare process, and so this is extremely difficult to detect it, but there are experiments which are going on, and they are giving limits. The Moscow Heidelberg collaboration is one of the most at the forefront of this thing, and and this particular process can only happen if neutrinos are Marana. I will maybe in future other set of lectures we can discuss a more greater detail about this aspect essentially. About so to summarize, neutrinos, one of the examples is that neutrinos are, there are a lot of details about neutrinos which I can mention, I can go about it, but this is one of the areas of my expertise, so I can talk a lot about it, but let me just say that neutrinos are have masses because we have discovered, seen their oscillations essentially. We have seen oscillations of neutrinos from one flavor to another. So, what we have seen is that electron neutrino getting converted to muon and tau neutrinos and so on. So, and that means that neutrinos have masses. Observing this is an experiment which we have seen, experimental observation. This has not only been seen in sun, but it has also been seen at accelerators, it has also been seen in the atmosphere, and so there are, it is now for present it has become a very well established that neutrinos, experimentally very well established concept that neutrinos oscillate, but we still do not have an experimental clarity because there are a lot of theories essentially. If neutrinos are Dirac like or if the neutrinos are Majorana like, there exist a lot of theories, and in both these cases neutrinos can have masses, but how do you distinguish? How do you distinguish whether the neutrinos are Majorana like or Dirac like? Now, the only possibility is to look at some process which are only possible for Majorana like picture, okay, and these are essentially possible, something like neutrinoless double beta decay. So, this is a process in which a neutrino transforms to its own antiparticle, and that transforms into, and so this only happens if so in this process neutrino gets transformed to its antiparticle, and that is the reason why it gives you 2 beta particles instead of 1 beta particle like in ordinary beta decay, and this all happens within the nucleus, and then when this happens you end up having you can prove that neutrinos are Majorana like essentially. Now, an important point, couple of corollaries about this particular aspect about neutrinos is that the Majorana nature of neutrinos is that I told you that neutrinos should be chargeless. That means they do not have any vector currents, cannot couple to so for Majorana neutrinos the vector coupling is 0 essentially. So, if you write psi bar Majorana gamma mu psi Majorana, this coupling is 0 essentially, where I put a m to say that it is a Majorana neutrino. This can be seen simply because you can take a Majorana neutrino, we have written the Majorana neutrino 4 component form, okay. Here you have taken a Majorana neutrino, just here we have write a Majorana neutrino, substitute it, put it a gamma mu in it, and you see that this just exactly goes to 0 for a current essentially. But you can have currents between 2 different type of Majorana neutrinos. Say if you have psi bar 1 Majorana neutrino gamma mu, psi bar 2 another gamma mu, this is not equivalent to 0. So, this is called transient Majorana current. We will see that for example, Majorana particles will not have magnetic moments, okay, because of this nature, because they for this reason, because their vector coupling is 0, they cannot couple to the photon, they cannot couple to any vector like boson, essentially they cannot couple to the photon. That means they have to be they have to be neutral. Again we are coming back to the same argument that they cannot, they have to be chargeless. If they have charge they can couple to the photon, if they are chargeless they do not have to couple to the photon, and so on. So they do not become. But you can have transient magnetic currents essentially. So you can have two different Majorana fermions coupling together with a gamma mu. This is typically not seen in our picture essentially. But suppose if you have a neutrino 1 and a neutrino 2, you can have a current between these two, say electron neutrino and a muon neutrino, you can have a current. And similarly this will lead to the concept of magnetic moments, which we will see once we study QED a little bit more. When we are studying QED we will see that there are something for Dirac fermions, the magnetic moments are predicted at least at the tree level, and the G minus 2 should be the gyromagnetic ratio should be equivalent to 2, half essentially should be equivalent to 2, and so then there are corrections to this gyromagnetic ratio, but for a Majorana fermion the magnetic moment vanishes essentially, but for a transient Majorana fermion, that means there are two different Majorana fermions, you can have a magnetic moment, you can have something called the transient magnetic moments. So these well, this is all, I am not giving you details, but I am just giving you a flavor of all these aspects about Majorana fermions in particle physics. They are extremely interesting because you have different current, different phenomenology associated with it, different signatures associated with them, and so they lead to a number of different features. The mass mechanisms are different, the currents carried, the quantum numbers, the conserved quantities, because Majorana quantum fermions break any electric charge, mass term breaks any U1 quantum number by 2 units essentially, like electric charge it breaks by 2 units, and that is the reason why you cannot have a Majorana fermion to be having a charge. So if you give a lepton number, the Majorana mass violates lepton number, Majorana fermions violate lepton number. Lepton number. So their mass term violates lepton number by 2 units essentially, their mass term So in any interactions Majorana fermions participate, there is a good possibility that lepton number could be violated if it is transmitted by its mass. So this leads to an enriched phenomenology of the Majorana fermions, and so this is pretty interesting essentially. Okay. So well, I will stop the this example. So this example of neutrinos, and in another example is in condensed matter systems. In condensed matter systems they are not fundamental particles, so the Majorana fermions need not be fundamental particles, but there are these emergent Majorana phenomena. Emergent means now as far as experiment is concerned, there is no difference between emergent particles and fundamental particles in real sense essentially, but okay, in in systems with many electrons and say some solids, essentially in systems with many electrons there could be some modes. So there are some standard modes like for example phonons, which are lattice vibrations and so on. So like magnons, which are spin vibrations and so on. So okay, but there could be some emergent phenomena which if you see the system in a different degrees of freedom, you see that these new degrees of freedom appear to be behaving like Majorana fermions essentially. So in some cases, in not all the cases, in some cases, so the examples are topological insulators, graphene and so on, so essentially. Now this is so the system is described best in terms of this emergent phenomena. So these emergent fermions. Now the main distinction between Majorana in the condensed matter systems and particle physics systems is the dimension of the system essentially. Condensed matter systems typically use Dirac like dispersion relation and everything in lower dimensions. So particle physics is always in 4 dimensions. So condensed matter is 1 plus 1D or 2 dimensions or T maximum. Most of the time it's 2D or 3D. Okay, so these are called low dimension systems essentially because you are always looking at 1 dimensional chain or a 2 dimensional surface or so on, so essentially, and so these are low dimension. Now you have to imagine that you can write down Dirac equation in these low dimension systems. How will you write Dirac equation in low dimension systems? So Dirac equation in low dimension systems so you follow the same procedure as previously. So you introduce, say for example you are only working in x and t dimensions. So what you do is you put in the dispersion relation to be E psi is equal to alpha x plus beta m essentially. So there is only one alpha and one beta, and impose the commutation relations between them, impose the same conditions essentially between alpha and beta, look for solutions, and then you end up having these classes of so exactly what we did in the previous in the first class essentially. So just to give you the Klein paradox. So what we did was alpha p plus beta m. Now exactly the same thing. Now instead of having p is equal to 1 dimension, so you only have one matrix, and now you iterate this condition, you iterate this condition, and you iterate this condition, and you will end up having the condition that alpha and beta should be anti-commuting, alpha and beta should be anti-commuting, alpha square should be 1, beta square should be 1. The same thing, you do the same process, and you look for solutions for this one essentially. So let me write it in terms of p essentially. So px, say for example px, okay, px and beta m and psi, and then this gives you solutions which are essentially your solutions for 1 dimension. Okay, now you will have solution, 1 dimensional solution. You don't have several solutions for here also, you have only one left movers and right movers and so on. So now there is a way of automating this purely in terms of Pauli matrices. You can use the Pauli matrices and now you iterate this thing, and this, so that this gives me E square is equal to p square plus m square. and so this gives you the conditions on this particular fashion. Now this is one way of doing it, but you can also do directly in terms of the polymatrices. You can, for each, you know that for each dimension you have to add one set of, every 2 dimensions you have to add one set of polymatrices, and there is a methodology of following this. And I will give you a reference where you can study how to write spinors in all dimensions, essentially even dimensions, odd dimensions, and so on. So essentially, now similarly you do the same thing for other low dimensional systems. Say for example, this is for 1 plus 1, you can also do it for 2 plus 1, and similarly. Now the odd dimensions are, if you increase by one odd dimension, the number of conditions will not improve. Essentially, say for example 4 and 5 dimensions, the number of the free solutions will not improve. Say between 1 plus 1 and 2 plus 1, then similarly you do not really have a larger number of solutions. It will be the same solutions with some differences. So you will miss some operators like chirality and so on. So, but the main difference in condensed matter systems is that how do Marana systems appear in condensed matter systems is because if you write everything in terms of if you write everything in terms of creation and annihilation operators, so you have one creation operator for the fermions and another creation operator for the anti-fermions. So what happens is that you have a situation in which you can have a linear combination of particle I did not come to creation and annihilation operators yet, so I am not really going into the detail. Particle and antiparticle or hole. So you will have systems like superconductivity or so, in which the system is best described in a Marana basis, in which the Hamiltonian is best described in a Marana basis. We will hopefully come to this creation annihilation operators in a couple of lectures later on essentially. So the Hamilton should go to something called a Marana basis, and in this basis you have this linear combination of particle and antiparticle or hole creation and annihilation operators, which are best describing the system essentially, which best describe the systems, and this is the best description of the system. So this happens in superconducting theories and essentially. Now another thing in condensed matter systems is this, the dispersion relation which appears is not, this is not actually C. Here we set C is equal to 1, but the C value is different in condensed matter systems essentially. So it is it's not equivalent to the speed of light, but it is some C, some constant, and that's all is what is readed. Okay. Now this is the other example in condensed matter systems, and this is the same thing. You can do it in graphene, and also similar kind of condition also appears in topological insulators and so on. So essentially, and there are several other examples in condensed matter systems, spin chains and so on. So which involve these Marana fermions. Okay, but we will not go into many applications. We have just seen them as examples just to give you the flavors of these two cases essentially in particle physics and in condensed matter systems. Okay, we will not go into more details in this particular set of lectures, but we will just see the flavor of these things, that Marinoff fermions are important in condensed matter systems and also in particle physics. So, given this, I will stop here, and from the next lecture we will start looking at more details about interactions for the Dirac fermions essentially. Okay, I will stop here. Thank you very much.